So in this video I'm going to talk through code we've written for 3 separate programs using C, written in MPLAB for PIC32 MX250F128D microprocessor from Microchip on a Fubarino development board, which I have connected into a custom development board that I've just put together on a Vera board. The first program we'll talk about here is just a basic analog to digital converter program. It reads in a 10-bit value from a pot connected to analog port 9, AN9. This then is displayed in 3 stages on LEDs 1 to 4. The LEDs 1 to 4 are on port C, but it's not the 3. The value is displayed firstly with the top 2 bits showing in the mid 4 bits, then the bottom 4 bits by blinking the LEDs in that sequence. There's a quick explanation here that you can see on the screen in the comments at the top there, just telling you how the program works. I sort of spoke about that. Just to move on into the code then, we've included PILAB.h where our peripheral library functions are, and this basically loads up any other header files that we need, int.h or standard IO and whatnot. Then we've got our configuration bits here, setting up all our different fuses for a 40 MHz system clock or 20 MHz peripheral bus clock. Firstly, we've chosen to use the primary oscillator, phase lock loop, high speed oscillator mode and peripheral bus divider set to divide by 2. To get our speed of 40 MHz, we use this second line here where we divide the input clock from the 8 MHz crystal by 4, then we multiply that by 20 and then divide again by 1, which gives us 40 MHz. The last line here is just a couple of other fuses that we're setting up, turning off the watchdog timer, setting up the in-circuit serial programmer to work for our PIC32. We've turned off the JTAG port and the secondary oscillator. A couple of hash defines here, just system clock, PB clock, and setting up 1 millisecond delay here, using system clock divided by 1000. It's just saying 40,000 clock cycles 1 millisecond. A few more hash defines here, which we'll come to in the main code. A couple of function prototypes, and then we'll go into our main function here. A couple of variables declared there, and we use this here macro here, system config performance, which basically gets the most out of our PIC. Then what I discovered was this actually changes the peripheral bus clock back to divide by 1, so I've added in this line here just to divide by 2 again to reset that back to our chosen frequency. Then we'll just set up a few, configure a few pins here for our inputs and outputs. Firstly, we select RB15, which is AN9. We set that to analog using this ANSL B line here, or the ANSL B register. We use the trace B register here, fill it up with 1s to set port B as an output. We send 1 to RB3, which has our transistor we have hooked up to our LEDs, and then we clear trace C, bottom 4 bits to act as outputs for our LEDs again. We call this function ADC configure, which we'll come to after, and then we go into this while loop here that runs forever. We call a value from the analog read function, which stores it then in top 2. Top 2 we send out to port C, and we mask the top 2 bits of that only. That'll be displayed there for 1/4 of a second. Then we clear port C, quick delay there for 1/10 of a second, and then we do the analog read again, store it in mid 4, display or shift mid 4 over by the amount we defined above here, send it to port C and mask the last 4 bits of it, and then same delays again, and then we'll do the same for bottom 4, and that just runs continuously. Then we come to our ADC configure and analog read functions here that we use, and there's also this delay MS function that I've written for our delays. So basically we're just sending bits into the add con registers here. We firstly clear it to turn off the ADC before we configure it. Send a few bits in here to configure it for like automatic sampling and setting voltage reference to these pins here, and setting up the acquisition time, and then we re-enable it at the end. Analog read then is past the value 9 above. That comes in here, this analog pin value as a car. This first line here controls which analog pin goes to the ADC, so we select this analog pin, shift it over by 16, and that goes to the analog to digital converter. We then begin sampling, quick delay in here while acquisition is done, and then wait while the conversion is done. When that's done, we return the value stored in this ADC1 BAF0, which is then fed back into our while loop up here. This last week function then is just a delay function to give us a delay measured in milliseconds using the timer 2 with a prescaler of 1 to 1. It's past the value in milliseconds, which comes in here. This value is T. T will decrement while it goes around this loop. So basically it goes into the loop for T times, and it will go through this delay, which is approximately 1 millisecond, and continue until T hits 0. And then I will stick in the video of this code working, and right after this you'll be able to see the lights, the LEDs lighting up as I turn the pot as it reads in a different analog reading. So this is our second program here. This uses a ring buffer. Basically it reads in, it's similar to the last program, it reads in the analog values determined by the value of the pot on AN9, stores that value in a ring buffer, and then the LEDs then output how full the buffer is. The ring buffer itself uses 3 variables, head, tail and count, which point to different locations in the ring buffer, which is basically just an array. Head points to where data is to be written, tail points to where it's to be read from, and count keeps count of how full the buffer is, and we'll use that variable then to determine what's displayed on the LEDs. So we've included the same header file. The configuration bits are exactly the same as before. We've added in this define T1 tick being 781, which I determined from this little calculation here to give us 10 milliseconds. A couple more just defining size of buffer size, and the buffer full is when count equals buff size here. A few more function prototypes, I'll come to these after the code, or after the main code. We've declared a few global variables here. The top one, buffer, is the actual buffer itself. It's just an array of buff size. Then there's our head, tail and count, all initialized to 0, and then we've this tick flag 0, which we set in an interrupt. So into our main code, we've got our system config performance again, then reset our peripheral bus clock divider. Then we've used this peripheral library function here to open timer 1. Yes, it turns on timer 1 Sets it up for internal clock source, 256 pre-scaler, and then period register is set to the value of T1 tick, which is 781. We then use this function here to enable interrupts, and using timer 1 as an interrupt source. We set our interrupt priority levels here, so interrupt priority level 2 and sub priority level 0. Then we enable multi-vector interrupts, and then finally enable interrupts. We configure pins here, input output pins, to analog or digital. So RB15 is again analog, port B set to be an output, turn on the LED transistor and then clear those bottom 4 bits to act as outputs for the LEDs. Another variable here, X, which we'll use down here for our analog value, or analog to digital value. Configure ADC and then initialize buffer, which is a new function which we'll talk about after. So we enter into your main while loop here. This just runs forever. So it'll continue checking if this tick flag has been set. If not, it'll just continue to cycle through. When tick flag is set, it'll enter into this if the statements inside this if statement here. It calls analog read. The value from it is stored in X. Then we send the value of X to this put data function here, which will store it in our ring buffer. Then to port C, we'll send the value of count, which we shift over 6 bits. So we just see the top 4 bits of it, and we also mask the bottom 4 bits of port C, so it's all we see. And that'll show us how full the buffer is. At the end of this, we just clear tick flag again. So tick flag is set in this interrupt service routine here, which is called every 10 milliseconds, which was determined by the this line here, open timer 1. So it's using timer 1 as an interrupt source. So basically we go into the interrupt every 10 milliseconds. First thing we do is clear the interrupt flag, and then we set this tick flag, which allows this bit of code here to run. So again, we're using a couple of the same functions we used before, ADC configure manual and the analog read function, which I explained earlier in the video. Then the new functions we have here is initialize buffer, which sets tail, head and count all to 0, and then we use this memset function here to write all zeros into buffer for the size of buffer, which basically just puts all zeros in buffer. Then finally we have this put data function, which allows us to store data in the buffer. The first thing it does when it is past an unsigned car, first of all it'll check if count is less than buff size, so it knows whether there's data to be written or not. Then it'll increment head to the next part of the array. Then checks whether it's full. If it is full, it'll set it back to 0. Then what we do then is store the value of data that's been sent to it into the head value of the buffer array, and then increment count and return 0 if that's successful. If count is equal to buff size, that means we can't write any data into it, so this will return a 0 to let us know that no data has been written. And then I will slot in the video of it operating just after this, so you'll see it. The LEDs will blink from 0 to 15 in binary to show the buffer filling up. Go for it. So our third and final program here is the UART program. It's sort of put together using techniques learnt in the previous 2 programs there. So it uses the analog to digital converter and also a ring buffer, but now we're reading in a value from a thermistor, storing that value in the ring buffer, and then we'll be displaying that value on the terminal. in hex, and we'll also be converting it to degrees value in decimal and displaying it on a set of seven segment displays. So what it does then is it displays the temperature on 7 segment displays, and it also displays how full the ring buffer is on the LEDs by counting from 0 to 15. These are all multiplexed together on the output port C. They're controlled by switching on and off 3 transistors on port B. We've included our same header file again. Configuration bits are all exactly the same peripheral bus speed, same system clock speed, the same T1 tick that we're using here again to set up our period register later in the program. Also with a few new ones here for buff size, buffer full, and what they are. Basically it's just telling this is buff size equals 1024, buffer's full with count is equal to buff size. And RE8 here, it's saved me typing that out later on. So you can see we have a few extra function prototypes in here, but when I come to them I'll explain what they are. Now what I've had to do here, beforehand the buffer was an unsigned car. I've had to change it to an unsigned int because the car was only an 8-bit sized word, where I was getting in a 10-bit value from the ADC, and it was cutting off the most significant bits, so I wasn't getting an accurate reading from that. I was getting roughly half the value it should have been, so my temperature display wasn't correct, and what I was receiving up on the PC terminal wasn't right either. Another problem I encountered with this program was the system config performance. Macro here actually changes the peripheral bus clock divider back to divide by 1. So I added in this line here to divide it by 2 again. Basically the divide by 2 up in the setup fuses up there is ignored by this, and it resets it, so always make sure I add this line back in. An alternative fix for that would be just to use the system config function instead of system config performance, and you can define which parameters you want to set up specifically using that. So we have a few new variables here as well, tens, units and digits, which I'll explain when we get to them. The next thing we'll do here then is set up our peripheral pin select, which sets up RB8 as our receive and RB9 as our transmit, using these couple of lines here. Then we configure the UART for 9600 baud. So we send 9600 to this function here, which again I'll come to in a second. We use the same open timer 1 peripheral library function here, and then we set up the interrupt source, priority levels, and multi-vector interrupts, all the same as before. The configuration of our input outputs here, we set port A up for being digital for the push button, set up RB15 to be analog, that's our thermistor, set up bit 8 on port A as an input using the trace register. We also clear the trace B register to make port B an output, but then afterwards we set RB15 back to being an input. For some reason when I set that up all in the one line it didn't really work, so I had to add this extra line in here. So basically cleared all of port B for output and then reset port B15 back to being an input. So then trace C clear, bottom 8 bits for our LEDs and 7 segment displays. So we call our ADC configure manual function again and then initialize our buffer. Quick delay here for the serial terminal, and then the first thing we do then is a couple of printfs to send out titles to the terminal with sort of the version, author, date and time, and just a quick description of what it is. So we enter into our main while loop next, then that just runs forever. Same as before, if the flag is set it'll read the ADC, store the value in X, and then copy that to the buffer, output to port C how full the buffer is. But now we've got a few extra things in here, these lines here which control our displays. So when we read in the value from analog read pin 9, store it in X and then send it to put data, it stores it in the buffer. The other thing I had to change then was on the put data, I had to change this to an int from a car, as it was truncating the value from the ADC. So back to where it was again there. we set up port B bit 3 to switch the LED transistor on, send out our value to the LEDs here, so the value of count shifted over 6 bits, send it to port B and mask the bottom 4 bits of it. We'll give it a 300 millisecond delay using the delay function, and then we use our y equals mx plus c equation to work out what our value is in degrees. So how I worked that out, I wrote a separate program here called Temp Sensor, which basically took a reading in from the ADC at room temperature, then it took another reading at the temperature of the thermistor at my fingertips, which was about 34-35 degrees. I sent the analog value from the ADC straight up to UART, made note of it at each temperature, took the differences of those, divided them. That gave me my value for this, which would be m in our mx plus c equation. X is the value from the analog read pin, and then to work out c here we used the temperature. So say for room temperature it would have been 22 degrees, so it would have been 22 degrees minus this times this equals this. So that's where I got this value. So back to our main program again here. Yes, so when we get y out here, y will be a decimal number of degrees. First thing we do is extract the tens and units from it. So we're using the modulus operator here, quick bit of maths, gets us our 10 and units separately. So the next thing I want to do is display them values in the 7-second display. So we'll switch on one segment here for units, and we'll send our units value via this digits variable to our segments function, which I'll explain in a second. Have a quick delay again, then we'll switch on the other transistor, send our tens value out to segments, and then another quick delay. You'll notice that this delay here is shorter than the other two. That's because the tens 7-segment display was lighting up a bit brighter than the units display and the LEDs, so I just for a quick fix made them light up slightly longer than the tens one here, just to make them look a wee bit more even. So we'll go down and talk about our segments function here. This is past the int digits, then it's used in this switch case statement here. So if it's past a 0, it'll send out the corresponding hex number for 0 to make up a 0 on the 7-second display. It'll do the same for 1 through to 9, and then that gets us our output on that. The last thing we'll do then again is just clear this tick flag. Then we enter into our next if statement here. So if not RA8, which is if the active low push button is pressed, we'll enter into these statements here. So we use a for loop first for 64 times, so I'll send our 64 values to the terminal via the UART. We call get data, which calls the current value of the buffer, stores it in an A, then we print F. So it's a 3-digit number in hex using A. So it'll run 64 times. I just added these couple of lines in here just to neaten things up on the display a wee bit. So it takes a new line after every 15th value, and then at the end, when I equals 63, which is the 64th value read out, I put in a full stop and 2 new lines, and then afterwards I print out the current temperature in decimal, which is in degrees, and then yeah, so that just continues to loop round and round. So if we get to our newer functions here, then get data, it wasn't used in our ring buffer code. It checks then if there is anything in the buffer to be read. It reads from the current value tail points at, stores it in C, increments tail, checks if tail is equal to the size of the buffer. If it is, it brings it back to the start of the buffer again for data to be written there. Decrements count and returns the value of C. If there is nothing in the buffer, it'll return a -1, which will show up as all Fs on the terminal if you keep pressing the button and catch up with the buffer. Then we set up our UART here for sort of standard operation, enable the transmit and receive lines. Set it up as 8N1, 8 data bits, no parity bit, or no parity and 1 stop bit. And it sent our desired baud rate, which was 9600. So I'll take 9600 in here. Yeah, I'll take 9600 in, and it'll enter it into our equation to get our actual baud rate out here. The actual baud rate then is returned as an int. Then we also have this MonPutC, which is a sort of custom function to let us use printf. It's the linker attaches it to the standard out header and allows us to transmit 1 character at a time of the UART. So I think that's every function covered there, all the code, so we'll quickly skip into a video of it running. So just to show what's going on the terminal side of things here, once the program is ran, first thing you'll see is the printf function sending up the titles to the screen. During this, the buffer is currently filling up with values, and the temperature sensor is sending through the value that's then converted into the temperature that's displayed on the 7-segment displays. Currently that's 19 degrees, so whenever I press the button here, it'll show up the first 64 values stored in the ring buffer plus the current room temperature. I can hit that continually here until the buffer empties out, and you'll see all F's there, so that's just sending us back out the -1 to show that there's nothing left in the buffer. So the buffer's now filling up again. I'm just going to hold the thermistor to heat it up a bit, and I'll read out the next temperature here then. So we're getting 28 degrees, and if I keep doing that, you'll see that the hex value has also got a bit bigger here. So yeah, that's that. So all the values there, they were all comma separated values. They could be then in turn inputted into an Excel spreadsheet, and you could put that into a graph to show how temperature changes over time. So like for example, you could maybe use that in a more practical application like monitoring the temperature in a room over a period of time, and maybe having a look at it on the graph, see how the temperature changes, and then you can maybe even expand it further to control the temperature in that room as well, maybe switching on and off a heater. But I think for the purposes of our project here, we've done enough. So I think to sum up then, we've learned how to implement the analog to digital converter, how to set it up, configure it. We've learned how to use the timers, also using the timers to control interrupts. We've also learned how to implement a ring buffer, how to fill it up and read from it. Also learned how to set up and write out to the UART, and also how to use some of the other peripheral library functions, different macros to set up, performance of the PIC. How to write out to the input-output ports, how to set them up for input or output for digital or analog, and of course how to set up the PIC itself for different clock speeds and different configurations using the #pragma config statements. So yeah, that's that. Thanks for watching.